Welcome to the semi-live stream of our physics revision. We've decided to do this video in advance because of the problems we had with it cutting out last time. But we'll still go through everything, take about half hour to cover all the main topics. So if I just get an indication when we're up to half hour and we'll wrap it up then. And we'll finish up, we'll cover what we can. For those of you who are in the sessions today, like my class, I did this session to my class, so you will have seen it. You can watch it again for a bit of a top up. This time you might be able to stop the video, pause it, make notes, or you can choose to just skip through to the bits that you want. Also, if you came into the theatre, did a session with me there today, again, you would have seen most of this stuff, so you will have the option of watching it again, seeing the bits you want to, skipping through, pausing, doing what you want really. But otherwise, moving on to the topic. P2, final exam tomorrow, last one for many of you in total. You get to leave afterwards, enjoy that break. Starting off with just a picture of a wave there. You could be asked to label up different parts of a wave. You were asked to do this last year, but for a longitudinal wave, this is a transverse wave. If those words don't mean anything to you, we'll come on to that a bit later on anyway. We'll talk about transverse and longitudinal waves. But the bits you need to recognise, you've got your crest, or peak, you can call it, the highest part, the trough, the lowest part, amplitude, which is the distance from the midpoint to the highest point, or you can do from the midpoint to the lowest point, either it's the amplitude, and the wavelength is the distance between two peaks or two troughs, either way around, or any 2 points on the wave, as long as you do the entire wave. So for example, you can do from here to here, that would be the same wavelength. You couldn't do from here to here, that is different, has to be on the way up there, to on the way up again over there. So that would be the wavelength. Jumping into forces. Forces is a big topic, came up last year, but it will come up again. You have different types of forces, should be able to name, but most forces come under just either a pushing force or a pulling force. They're the main two, which you can sort of bracket most forces into. Some are contact forces, mean you have to be in contact with an object to exert a force on it. Some are non-contact, they don't need to be touching to exert force on each other. So a magnet will exert a force at a distance on another magnet or magnetic material, either attraction, if it's opposite poles, or repulsion, if they're like poles, that is a force. If forces are balanced, there will be no change in motion, so the object will continue to move at a constant speed. That can mean a constant speed of 0, so constant speed of 0 is a constant speed, means there is no resultant force acting on me right now. My forces are balanced, and balance is a key word. If you're talking about forces, you want to talk about forces being balanced or being unbalanced, as in this second scenario here. If forces are unbalanced, then there will be a change in motion. That, to you and me, means acceleration. The object will accelerate. If the forces are unbalanced, there will be a resultant force, and the resultant force is what leads to acceleration. In this scenario, if you can see it from where you are, we have a lorry or truck moving with 100 newtons of force moving forward and 60 newtons of drag force pulling it back. To find the resultant force, we would do one force, the bigger force, subtract the smaller one, so 100 subtract 60 means we have a resultant force of 40 newtons. All forces are measured in newtons. So we have 40 newtons, but you also need to say that 40 newtons is to the right, and that means the truck will accelerate in that direction. If we didn't know the force, but we knew the mass of the truck and we knew the acceleration of the truck, we could use this formula, really important formula. Force is equal to mass, measured in kilograms, multiplied by the acceleration, measured in meters squared, per second squared, meters per second squared. The meters per second squared is part of the units. It does not mean this number has to be squared in any calculations using this. It is just part of the units. Do not make that mistake. So if we knew the mass of this truck, we knew the acceleration, we could work out the resultant force acting on that truck by doing force is equal to mass times acceleration. Just one of the many equations you have to remember for physics. Weight and mass are linked together. They are not the same thing, even though normally they get confused by most people. In science, we consider the mass of the object to be the amount of matter that makes it up, and is measured in kilograms. Mass is always measured in kilograms. Gravity It's different depending on where you are. If you're on Earth, gravity is usually rounded to around 10, but they will tell you what value to use in your exam paper. It more than likely will be 9.8 newtons per kilogram will be the value for gravity you are using. If you know the gravity, so on Earth, let's just call it 10 for now, and we know the mass of an object, my mass is about 95 kilograms. If I do 95 multiplied by 10, I get 950 newtons. My weight, the force pushing downwards, based on gravity, is equal to 950 newtons. So mass is the amount of matter that makes you up. It does not change no matter where you are in the universe. Okay, your amount of matter stays the same, and it's measured in kilograms. Whereas your weight is a downwards force dependent on gravity, and that can change. Forces link into this topic, which is about springs, or specifically a thing called Hooke's law. This is a required practical, which did not come up in the paper last year, so it's maybe something that will feature this year. You should have done this practical. It involves you attaching a spring to a clamp stand. Those are the metal like stands and the little clamps that stick out. You attach a spring to that, and you would hang masses off of the spring and see how far it extends. This is a ruler that runs alongside your spring, so you can measure the extension. Remember, you are measuring the extension, that's how far the spring stretches, rather than just the length of the spring. Because even when the spring is relaxed, i.e. there is no force on it, it will still have a length. When you add masses or apply a force to the spring, it will stretch and it will get longer. Okay? As you add more force, the spring will extend further. There is actually an equation you need to know that links this together. If I stand over here, you might be able to see it a bit better. So the force applied to the spring in newtons is equal to K, which is called the spring constant, multiplied by the extension of that spring. The spring constant should be newtons per metre, and the extension should be in metres if we're doing this correctly using standard units. So, when you add more force, the spring will extend further. Once you've done this experiment, so you've set this up, you've measured your length of your spring, added masses or increased the force, measured the length as the length of the extension as more force is applied, you may plot a graph that's like this. This is the force, and on the bottom, now it's called weight because weight is the downwards force because those masses are hanging here, so the downwards force pulling them down is obviously weight created by gravity. And this is the extension plotted along here. We can see from this graph that as we increase the force, the extension of the spring also increases. If we're to rearrange, if we wanted to find, so if we'd done this experiment, we've got the extension and we've got the force, we don't know at this point the spring constant. To find the spring constant, we would do the force divided by the extension would tell us the spring constant K. And what we can also tell from this graph is the limit of proportionality is reached for this spring. This means if we increase the force acted on that spring, it increases by a set amount. Every time we increase the force by 0.5 newtons, it increases by the same amount each time. In this case, 2 centimetres. So 0.5 is 2, 1 is 4, 1.5 is 6, 2 is 8. So every time we increase the force by 0.5, we're increasing the extension by 2 centimetres. Up until this point where we've reached 2 newtons. When we reach 2 newtons, it's the limit of proportionality. If you want to think about it in concrete terms, it's when the spring actually becomes stretched so far that it becomes deformed and will no longer return to its original shape. You've probably done this with a spring before. If you pull it out, let it go, it springs back. If you pull it too far, it becomes stretched and it no longer returns to its original shape. Often happens to slinkies and things like that. Maybe you've taken the spring out of a ballpoint pen before and stretched it to the point where it no longer returns to a spring. It's deformed and no longer returns to its original shape. You could also use this, if you go back to P1, so a lot of things come up from P1, to calculate the elastic potential energy. If you know the spring constant and you know the extension, you can calculate the elastic potential energy stored in the spring at any point. Now, the equation for elastic potential energy is one of the ones given to you on the formula sheet, so you will have access to that in the exam. They can in the physics do what's called multi-stage calculations, more likely to be in the higher paper, where you have to use one calculation to find something. So maybe you would use this calculation to find the spring constant based on the practical, and then you would use that spring constant to calculate the elastic potential energy stored in a spring with a certain extension. Moving away from forces, but linked, forces are linked to motion, because if forces are unbalanced, it leads to a change in motion. We talk about speed and velocity. Now, speed is what we call a scalar quantity. It just has size. In science, it's measured in meters per second. The units are important. I will talk about this again, and I've talked about it lots before. They are likely in the paper to give you some of the numbers in the incorrect units. For example, rather than giving you a distance in meters, they'll give you a distance in kilometers, which is 1,000 meters. Instead of giving you a time in seconds, they'll give you a time in minutes. You need to times the minutes by 60 to find the number of seconds. So be aware, you have to be able to convert units from one thing to another, and the standard units for distance are meters, standard units for time are seconds. Speed is how fast an object is travelling, doesn't matter what direction, it's just how fast it's going. Whereas velocity is what we call a vector. Velocity is how fast an object is travelling in a certain direction. So if it's travelling in 10 metres per second that way, it's different towards 10 metres per second that way. There are different velocities, same speed. You can calculate the speed, or we could say velocity, particularly if we change this for displacement, by doing the distance divided by the time. So speed is equal to distance divided by time. Okay? So remember that, but remember the units need to be metres and seconds. Acceleration is the change in velocity of an object divided by time. How fast it's accelerating is how quickly it's changing its velocity. You could say an object's accelerating, which means it's getting quicker, or decelerating, which means it's getting slower. Deceleration is actually a negative acceleration. And you could be asked to work out deceleration. Now, for deceleration, you need to remember your numbers will end up negative. For example, if an object's travelling at 10 metres per second, and it slows down to 0, the change in velocity is actually minus 10, because it's gone from 10 to 0. It's decreased by 10 metres per second. Okay, so remember that. If your final velocity is slower than your initial velocity, your answers should be negative, because it's deceleration. I mentioned this already, but I said I'd mention it again, or will mention it again. The units for acceleration are meters per second squared. Okay, they're meters per second per second. The reason that's important is because you do not square the number. This is just the units that are used, meters per second squared. Also in the physics, they do occasionally drop in questions where you have to do a calculation and then you have to quote the units. So do remember the units for different numbers that you would deal with: forces in newtons, energy in joules, speed or velocity in meters per second, acceleration in meters per second squared. Those sort of things are worth remembering, because they can ask you the units for different bits. There is a required practical on acceleration. Now, I will say this did come up in a bit of detail last year, so it's less likely to this year, but again, it's just a gamble. Whether it does or doesn't really, can't guarantee. This practical involves using a trolley, sometimes on what we call an air track. Now, an air track is to reduce the friction that's acting, but it has a pulley attached to some masses here to provide the force. The force pulling this down, again, is the weight, but it's because it's attached, it's also the force that's pulling this object forward. These light gates can take the time it takes to travel that distance between these 2 points, but they can also, because the mask size, which is this bit here, is 1 centimetre, time the distance it takes for that 1 centimetre to pass through the light gate, and hence give you a speed. So they can tell you a speed here and a speed here. So you could take the final velocity and the initial velocity to find out how fast it had accelerated between those 2 points, or if you knew the force, because you knew this, you could work out the mass of the trolley. There's lots of things you could do with it, but they will give you some data in that experiment as well. But that's the setup. Remember, you can draw diagrams if you're asked to talk about practicals, and the light gates measure, depending on what you're trying to find, the speed or the acceleration. They can measure a speed, or they can measure the time taken to travel the distance between them. Distance time graphs. This is one type of graph we come across in this unit. You can tell this it's got distance here. Now this should say meters as well. The units would be meters, and time should say seconds. Distance time graphs, there's lots of lines on here, but they tell us different things. If it is a straight line, straight diagonal line, it means the object is moving at a constant speed. The steeper the line, the faster the object is moving. This line here in green is faster than this line in red. If it is a flat horizontal line, it means the object is stationary because the distance is not increasing no matter as time goes on. If the line goes downwards, then it shows that object is returning to where it started. So this object has moved away from a point, stopped for a while, and then come back to the same point. If someone was getting to the same point, the same distance, but took longer to do it, you may have a line that travelled like that, travelled the same distance, but took a longer length of time to reach it. They sometimes get you to make a comparison between two objects, a car and a cyclist. They travel the same distance, so they need to get to the same height in the graph, but take a different length of time to do it. You just need to look at the distance they need to travel, look at the time it takes them, and draw a line there. This curved blue line shows that the object is accelerating or getting faster. If the line is curved, there is acceleration. If it's curved upwards like this, that's getting faster, i.e. accelerating. If it was curved, if my curve was like that, that would be decelerating. And eventually, when it was flat, it would be stationary. The other type of graph you can get is a velocity time graph. This can be seen because rather than distance on the y-axis, we have velocity in meters per second. This does not show the same thing. Rather than showing constant speed by a straight line, it shows constant acceleration. So a straight diagonal line shows constant acceleration. This line in blue is accelerated faster than the object in red because it reaches a higher velocity in a shorter period of time. So therefore, the steeper the line, the faster the acceleration. If it is a flat horizontal line, then it shows constant velocity, i.e. that object is moving at a constant speed or velocity of 8 meters per second. We can work out the acceleration from this by doing the change in velocity. So from 0 to 8 in 4 seconds, that has accelerated. Change in velocity is 8, time taken is 4, 8 divided by 4, 2 meters per second squared. That red line is accelerating at for that point. If the line goes down, it doesn't show that the object is returning to where it started. It shows that the object is decelerating because the velocity is going from 8 meters per second back down to 0, ends up at 0. And it takes, this time, 3 seconds to do that. So it is decelerated quicker than it accelerated on this red line. It will be 8 divided by 3 in that instance for the deceleration. Thing I'd have to bear in mind for the deceleration though, because it's gone from 8 to 0, that would be 0 minus 8, which gives us minus 8 divided by 3. We should get a negative acceleration because it's decelerating. With this, I will just say, I won't go into great detail, you can calculate the distance this object has travelled by taking the area under the line. You have to split it into sections. If I split it into this triangle, this rectangle and this triangle, I can work out the distance this object has travelled. You need to just work out the area of a rectangle is the base times the height, and the area of a triangle is the base times the height divided by 2 at the end. So work out all the areas of all the different sections. I'd actually draw the lines to divide it up and then add the different sections up to get your total distance. Falling objects. If an object falls and is under the effects of gravity as it's falling, i.e. skydiver or any object dropped from a distance, then initially, as soon as the object begins to fall, the only force acting on it will be its weight or gravity pulling it towards the centre of the Earth. The faster an object travels, the more drag forces act on it, i.e. the more air resistance there is. The faster you're going, the more air resistance there is. So as this skydiver accelerates, or I should have said, at this first stage, stage A, because the only force acting on him is gravity, i.e. his weight, and there is no opposite force at this point in time, the resultant force is down and is a large resultant force going down, meaning he will accelerate because forces are unbalanced. As he accelerates, he gets faster and the drag force starts to build up. But in this second diagram, there is still a resultant force going downwards because this is still a greater force than the upwards force of air resistance, so he is still accelerating. He is accelerating less now than he was initially. As he gets faster and faster, the drag forces increase, air resistance increases to a point where the drag forces become equal with the weight pulling him downwards. At this point, because forces are now balanced, it means he continues to move at constant speed or constant velocity at this point when forces become balanced. Now, if he was to open his parachute, I should say, when he's reached that point where the forces become balanced, he's moving at constant speed, we say he's travelling at terminal velocity. If he wanted to increase his speed, i.e. accelerate again, he would need to reduce drag, maybe by making himself more streamlined. Once he opens his parachute, his weight is not going to change. His weight won't change no matter where he's falling, because his weight is his downwards force based on his mass. But if he opens his parachute, drag increases because of the large surface area of the parachute. So drag will increase massively, it will be bigger than his weight, causing a resultant force in the upwards direction. At that point, he will decelerate rapidly. He won't move upwards, he will decelerate. As he decelerates, his velocity falls, and that causes the drag to fall, because the slower you go in, the smaller the drag forces get, or air resistance gets. Eventually, it will reach a point where the drag forces have got smaller and smaller, and they are equal to his weight again, both at 600, and he will reach a new terminal velocity, which was slower than his original terminal velocity. On to waves. Two types of waves I mentioned. We have longitudinal waves. Longitudinal waves, if you're asked to describe them, they have vibrations or oscillations which are parallel to the direction of energy transfer, meaning the wave is transferring energy or moving in this direction, and the vibrations are back and forth parallel to them. Transverse wave is one where the wave is travelling in this direction and the oscillations or vibrations are 90 degrees, i.e. up and down in the direction of transfer. So as the wave moves that way, the vibrations are up and down. So at 90 degrees perpendicular or at right angles to the direction of transfer. The only longitudinal wave that they really bring up is sound waves, and the majority of the other ones you talk about are transverse. Light and all of the waves in the electromagnetic spectrum are transverse. Another equation you need to know, the wave equation, the velocity of a wave is equal to the frequency times the wavelength. So that's another equation to remember, and one that you're not given on the equation sheet. Linked to waves is a required practical. The third required practical we talked about, so Hooke's law, the spring, the acceleration of a cart, and then this one is called the ripple tank, which is the third required practical. This one wasn't asked about last year, so could be asked about this year, but isn't a very nice practical in my opinion. There's not a lot you can investigate for it, except for changing the speed of different waves that are coming out from this apparatus, but it's a bit fiddly to get to work. Essentially, it is a shallow tray, usually made of glass, with a wooden block or board across it with a motor attached. When you attach that motor to a power supply and turn it to a low voltage, it will make the board move up and down in the water, which will create waves which pass along the water. If you shine a light through, you will get the shadow of that wave pattern on the floor, so you can actually see the pattern of those waves. Then based on this, you can work out two things, the frequency and the wavelength of those waves, put it into wave equation, and you can work out the speed of those waves. The best way to work out the wavelength is, this is what it would look like on the floor. You could try to see where one wave started and another wave started and measure the distance between them, that would be the wavelength. But I would advise you to say, you would try and measure the length of about 3 waves, and then divide your number by 3 to get the wavelength of just one wave. It would be easier or more accurate to measure the distance of 3 waves and actually then get a value for that. Frequency, similarly, it's quite hard. Frequency is the number of waves that pass by a set point every second, every 1 second. It's quite hard to measure that. So instead of trying to measure the number of waves that pass a point every second, I would put a point on the floor or a line on the floor, start a stopwatch, count the number of waves that pass in 10 seconds, and then I would divide my number by 10 to find the number of waves that pass every 1 second. That may not be a whole number, because it doesn't have to be a whole number, the frequency. It could be 1.5 waves pass every second, or the frequency of the waves is 1.5 waves per second. Frequency is actually measured in a unit called hertz. Hertz stands for vibrations per second. Reflection of waves is just a wave comes in, it bounces off a surface, and it bounces off at the same angle it comes in at. The normal is aligned 90 degrees to either a plane mirror or to a glass block or some other apparatus you are shining a ray of light usually, but it can be any wave at. Refraction, I'm not going into great detail on, but essentially refraction, because waves change speed when they go from one medium to another, or even water waves change speed when they go from one depth to another. If they hit at an angle, they get bent or refracted. They change the direction they are travelling, and then when they leave, they go from glass to air, the speed changes again, and they're refracted again as they pass out. You need to know your waves in the electromagnetic spectrum. The way I have for remembering it is remember my instructions visible under X-ray goggles. Radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. Okay, that's the order. As you go along from that order, the frequency increases and the wavelength decreases. It's good to know one use of each of the waves in the electromagnetic spectrum. Radio waves are for communication, microwaves also for communication. They're used in mobile phones, but also for cooking in microwave ovens, which is your microwave. Infrared is used in remote controls. Visible light for seeing. Ultraviolet, used in sunbeds, tanning booths. X-rays are used for medical imagery, which is to see bones. And gamma rays are used to treat cancer. Their main uses. All electromagnetic waves are transverse. They all travel the same speed in a vacuum, which is the speed of light, and they all transfer energy from one point to another. The last thing I'm going to talk about is just the required practical to do with infrared radiation, because it didn't come up last year. Infrared radiation is emitted by objects that are hot, and they emit infrared radiation. And you can make an object either absorb or emit more infrared radiation by making the object black, which means making it a dull colour, as opposed to white would be the opposite, which reflects infrared radiation. Make the object matte, which means make it dull, which means it's not shining. And the opposite would be shiny. Matte objects absorb more infrared than shiny objects. And if you increase the surface area of the object, that will increase the amount of infrared radiation it emits or absorbs. The required practical is this. The required practical could involve, this is quite sophisticated, well I say it's sophisticated, it's not that sophisticated, it's called a Leslie cube, so if you come across it in the exam, it is just a metal cube where you place hot water. It has 4 different surfaces, shiny black, matte white, and a shiny white or silver surface. And you use an infrared detector. So when you put hot water in here, you detect the amount of infrared radiation that is emitted by these different surfaces. So you'll check the shiny silver, check the shiny black, check the matte white, check the matte black. If we've done the experiment correctly, the matte black should emit the most infrared radiation. You can do a less sophisticated version of this just by using test tubes. If you used a test tube, but surrounded that test tube in black card, you could have shiny black card, dull black card, shiny white card, dull white card. You could put a thermometer in the test tube, place some hot water in there, and see which test tube loses the most heat. The test tube that loses the most heat emits the most infrared radiation. Okay. This is where I'm going to stop. Could go into the motor effect. It is only on the higher paper. The motor effect is something that didn't come up last year, but is in the higher curriculum or syllabus or specification, I should say. So I do expect there to be something on the motor affecting this year's exam, but I can't guarantee that. So do look into that if you're sitting higher. Last of all for me is just to really say that these are the equations that are found in the forces topic. You do need to know these. Freeze it, pause it now, take them down if you don't know them already. And these are the ones in the other topic, so waves and magnetism, electromagnetism, although this one's only in the higher unit. So hopefully you can pause that, take it down if you haven't got these already. And just a shout out, because I do these at the end, and this is the last one I'll be doing for this set of exams. So shout out to the Glasses gang. I was supposed to say it 3 times, I think. So Glass gang, Glass gang, Glass gang. Done that. 11Y1 been an amazing class this year, so shout out to the whole class, but particularly Prashana asked me to shout out to them. Shout out to Yasin, who's been brilliant, and the NIK, Nikesh. He said something like, I think I'm getting this right, he was the funniest looking student in year 11. I'm pretty sure that's what he said to say, so hopefully he sees this. Okay, otherwise, good luck for your exam tomorrow. Come in early and we'll be there to help you, and then it'll all be done and you can enjoy your break. Best of luck, guys.